Hello, everyone. My name is ANDREAS Lumenta. I am a student in Class C of the Information Systems program at Sam Ratchalangi University. Today, I will be presenting my second assignment for the graph theory course. The topic we will discuss today is the concept of the crossing number in graphs, complete with visual examples.
In graph theory, the crossing number of a graph G, usually denoted as Craig G, is the minimum number of edge crossings that occur when the graph is drawn on a plane. Here are the key points for understanding this concept. A crossing occurs when two edges of a graph meet at a point that is not an endpoint. The goal of finding the crossing number is to draw the graph in such a way that the number of such crossings is minimized. If a graph has AC trig G equals 0, then the graph is called a planar graph. It can be drawn without any edges intersecting. If TRG is greater than 0, then the graph is non-planar. Some well-known graphs have a fixed crossing number, complete graph K. This is the smallest non-planar graph in which every set of 5 vertices is connected to one another. The value of CRK5 is 1. Complete bipartite graph K, 3, consists of 2 sets of vertices, 3 inches each, where every vertex in set A is connected to every vertex in set B. The crossing number CRK33 equals 1. Calculating the crossing number is generally a very difficult problem in computer science. No problem hard. However, there are several inequalities that help provide estimates, one of which is the crossing lemma. If a graph has a number of edges A that is much larger than the number of vertices, V specifically, if E is greater than 4V, then kringon 64 times E quadrado. This formula shows that the denser a graph is, the more edges it has relative to its vertices, the more the number of crossings will increase significantly.
The concept of crossing number has wide-ranging practical applications, particularly in the field of technology, integrated circuit design, VLSI. When designing computer chips or printed circuit boards, PCBs, the crossing of signal paths is avoided or minimized as much as possible to prevent signal interference and manufacturing complexity. Data visualization. In creating complex network diagrams, minimizing crossings makes the diagrams easier for the human eye to read. Knot theory, related to how a geometric structure can become trapped or entangled in three-dimensional space. In addition to flat surfaces, scientists also calculate crossing numbers on other surfaces such as rectilinear crossing number, where every edge must be a perfect straight line. Toroidal crossing number, the minimum number of crossings when a graph is drawn on a donut-shaped surface, torus.